Okay, so good afternoon, everybody, and pleasure to start the afternoon session. So, so this talk is about expected float entropy minimization, which is a relationship content theory of consciousness. So it's going down the relationship route. So this is kind of like what we're going to be doing today or this afternoon. First of all, we're going to basically try to make the case for a mathematical formulated relationship content theory of consciousness. And then I'll provide a kind of motivating example or problem which isn't perfect, but its imperfections are quite useful for telling us what we should actually be doing. So it kind of helps to provide some motivation. And then I'll actually introduce expected float entropy minimization, provide some examples, talk a bit about machine learning perhaps, and we'll see how far we get through the last few bits at the end there. So to start with, however, just a few observations really about information and the brain. So information on its own usually doesn't have a lot of meaning to it. So for example, if I ring up my friend in Australia and my friend says to me, the weather today is an 8. That doesn't really mean very much to me, but if I know in advance that it's from 1 to 10 and 10 is a really lovely day, then suddenly that bit of information means something. It means that it's a really, it's a pretty good day today. So arguably, you need to have context in order for information to acquire meaning. So when we think about the brain, the brain is full of information. So you take a brain state, all of those neurons in their different states, that's full of information. And consciousness is full of meaning. So perhaps what's missing there is context. So we're looking for how the brain somehow defines context here. So just this statement here, content of conscious experience might be the meaning that brain states have relative to some context, but then, how are we going to do this? Where's this context coming from? So I'm going to sort of be arguing that the context should be to do with relationships, perhaps. So we're looking for a kind of theory for how the brain defines relationships, which give us our context. So I'm going to give 3 arguments in favor of a mathematically formulated relationship content theory of consciousness. So the first one is that the brain itself has to make extensive use of relationships. And so, for example, the brain does a lot of filling in. The brain gets information from the senses. It's often quite noisy and it cleans it up a lot. It uses relationships between things which it's already learned, and it fills in missing information. Machine learning also does lots of, makes great use of relationships between things as well. And you might have a really bright student who says, well, why do we bother with relationships? Why don't we just use probabilities and use sort of Bayesian methods instead? Why doesn't the brain just do that? So in this argument, I'll kind of explain why the brain must be using relationships. So this is sort of Bayes' theorem here, and we have some evidence here. So this is the evidence for what the state of the outside world looks like, and the brain has to kind of fill in this missing spot here. And we have some hypotheses across the top of what we should fill in. And the first hypothesis is really bad because it doesn't even agree with the evidence. Then the next one has got this cute picture of a cat filling in the blank. So that's better, but it's not quite right. And then, of course, this one is the right one. But, of course, the thing is, without relationships, we don't even have images here. We have to see these things as just huge vectors. So there's no house there, there's no colors, it's just information. And there's a lot of possibilities. So if that was a megapixel image and there was just 10 possibilities per pixel. You've got 10 to the power of a million possible images there in this space of all possible images. And well, the brain's not going to sample the world enough to know what the probabilities are. So all the time, you're just going to be coming up for the first time for having seen that vector. You've never seen it before. So you have no idea what the probabilities are for that vector. So you can't really apply Bayes' theorem to it because you just don't know what the probabilities are. So the brain instead, it has to use relationships between things. When you have relationships, you have things like images, you have objects, you have colors, and then you can extrapolate to things which they look familiar, but you've not actually seen them before, and the brain can fill in missing information. So argument number one, the brain must be using relationships a lot. Okay, so argument number two, consciousness itself is full of relationships. I'd say that our conscious experience is awash with relationships. So as I say, without relationships, you don't even have, sorry, oh, I pressed the wrong button. Okay, so without relationships, you don't even have images. So we have relationships which give us images. We have relationships between colors. I would describe these kind of relationships as kind of being primary ones. So they're not at kind of higher levels where you're talking about relationships between objects, things that emerge. They're kind of primary. They allow you to actually have images and to have sound, etc. So the next one was to do with sound. So you have relationships between frequencies. We experience frequencies that are very similar as being indeed similar. So and also with harmonics. So we can hear that there's a relationship between two different frequencies if one is a harmonic of another, and also in terms of amplitudes as well. We can all agree that two things are both very, very loud, even though they're very different. So kind of our experience of sound is also full of relationships. And then once we have these kind of primary relationships, you can go up to more complicated things, and you can have relationships between objects and nouns and tastes and textures, places and other objects and so forth. So these kind of relationships, I would say, are kind of secondary. They're what you can then do once you've kind of got images and so forth in place. And I'd say it's really hard to think of any kind of conscious experience, although we were trying to do it before lunch in our discussion group, and maybe we did get somewhere, but it's generally pretty hard to think of conscious experiences which do not contain lots of relationships between things. Okay, so that's argument number two, for a mathematically formulated relationship content of theory. Consciousness has got lots of relationships in it. And then finally, well, it's a mathematical formulation, and of course mathematics is all about relationships between things. So algebraic operations, functions, metrics, topologies, graphs, these are really all just relationships of one sort or another. So mathematical structures are kind of made out of relationships, really. So maths is the kind of perfect thing for developing such a theory, I think. So that's kind of my three arguments for why we should try to do this. Next is some motivation. So this is called the definitive player problem. Roger Penrose in a meeting recently described it the memory stick from Mars, perhaps, which is I rather like that. So basically, this is going to try to show us the direction we should go in, give us some intuition, I guess. But it's not a perfect example, and its imperfections are going to be useful. So imagine we have a stack of CDs. These are all music CDs. They all encode a step function representation of a wave function using the same encoding. And each disk is made to some kind of generic template. So the actual locations where information is stored on the disks, it's the same for all of the disks, albeit what actually is stored at a given location. It will depend on which disk you're looking at. Okay, so imagine I take the top disk from this stack of disks, and I think of my favorite tune, whatever it is. Well, I can work out what I need. I can say for my favorite tune, I need, first of all, I need a 0, then I need a 1, then I need another 1, then I need a 0. And I can just cherry pick a path through the disk, going from one point to another point, such that I get the values that I need. That I get a 0 first, and then a 1, and then another 1, and then a 0. And basically what I've done is I've designed a player, or I've picked a player, and when I put the disk into that player, it's going to play my favorite tune. Okay. But what happens when I take the second disk in the pile and put it into that player? You're probably going to get white noise out of it. So what we can do, so basically what I'm trying to say here is that really the first disk, it doesn't have a lot of meaning to it, right? I just picked my favorite tune. It could have been anything. So it doesn't have a lot of meaning on its own. However, we could do something else. What we can do is we can say, let's choose all of the players for the top disk that give highly structured output, low entropy in some sense. And we can then do that for the second disk and the third disk and so on. So for every disk, we get a subset of all the players, the ones which give you highly structured output. And then what we can do is we can take the intersection of all of those sets of players. And if our stack of CDs is actually deep enough, if we've got enough of them, then you're going to have just one player left, and that's going to be the definitive player. And relative then to the stack of CDs, now your disks do have meaning. So now, it won't be my favorite tune anymore, but all of those disks are going to play their tune. And somehow, in the context of all of these disks, the disks now do have a specific player meaning to them. Now, as I said, this example it has some problems with it because there's some assumptions involved. First of all, we were restricting ourselves to a reading order on the disk. Well, that's just kind of like a relationship between the points on the disk, which gives you just a line of points. It's just kind of one-dimensional. You're going from one point to the next to the next, one node to the next node to the next node. But there's no reason for that. It could have been images on the disk, which would be two-dimensional. So you need a theory which doesn't assume what that graph is going to be. It can be any graph to start with, any structure. And also, with regard to playing the disk, you're also assuming that there's a structure on the bytes as well, because they're giving you the steps in your step function. And we can't make those, when we want to have a general theory which can apply to the brain, we can't make assumptions about the relationships. We need to have those come out. Okay. So here's a few observations. We need a general theory based on relationships that can be applied to any system, whether they be natural or artificial, involving nodes and node states. No relationships can be assumed a priori, so we just mentioned that. The theory must be derived, the theory must derive the primary relationships, which are the relationships between the nodes and also between the node states. For the brain, the nodes can be individual neurons or larger structures, so we don't necessarily take the nodes that we're interested in to be individual neurons. They could be tuples of neurons or larger structures. Again, we mustn't assume that there's any particular structure on the states that the nodes can be in. And the theory needs to be able to be extended to include relationships between features that emerge once you have the primary relationships defined. Okay, so that's got a few things to think about there, kind of constraints on how we should develop such a theory. Okay, so I'm going to spend a little bit of time on this slide, and Looks a bit mathematical, but it's actually very straightforward, and I'll explain. So this is float entropy. What we actually have here is this SI here is a system state. So we can think about brains now, perhaps, or cortical regions. That's a system state. Now, what is actually a system state? We can think of it as being a function. We have some nodes, and they're going to be mapped to the state that those nodes are in. So we've got a set of nodes, and we've got a set of possible node states, and we've got a system state, which is then a mapping from the set of nodes to the set of node states. So kind of SI, you can think of it as being like a function. And then we got this R and U. Well, and these are just parameters on this side, so we can choose what these are. And R is basically a structure that we put on the set of nodes. U is a structure that we put on the set of node states. So it could be a weighted graph, it could be a topology, it's something to do with relationships, it could be a metric perhaps, but it's basically something to do with relationships between the things. So what does all of this mean? So what number do we actually get out of this? Well, ignore the log for a moment, don't worry about the log. Basically what this is the number of system states that are at least as continuous as the system state SI is. So we're basically counting how many system states are as continuous or even more continuous than this state SI is. We can talk about continuity because we've got structures on the domain and the codomain. And so that's basically what that is. Now, of course, the theory isn't of float entropy, it's about expected float entropy minimization. So basically, your system is biased towards being in certain states. So remember the stack of CDs, they weren't just random CDs, they were a specific set of CDs. So your system, your brain region, through learning or whatever, it's biased towards being in certain states. And that bias can be represented as a probability distribution, and that allows you to take expected quantities. So we can take the expectation of float entropy. And the theory is this of minimization. So we can then take that expected float entropy, we can use it like an objective function, and we can look for the parameters R and U, our structures, our relationship structures, that then give you the minimum expected float entropy. So what does that achieve? Why do we want to do that? Well, if I have a system state that's highly probable, then it means that relative to R and U that minimize expected float entropy, it's going to be very continuous, it's going to be highly continuous, and in particular there's going to be very few other system states that are more continuous than it is. Why is that important? Well, it's important because we're looking for the relationships which are important for this system rather than just some arbitrary system. We're not talking about some other system which has a different probability distribution. We want to pick out the relationships which are important for this system. So the probable, highly probable states, once we've done this float entropy minimization, we will have found R and U for which they are in particular highly continuous relative to other system states. Okay, so it's a way of extracting the relationships which have got something to do with the system that we're interested in. Now, I'll just move on. So this next slide, it kind of says what I've just said, really. So that's just taking expectation, there's the probability. Here we're doing the minimization, so this is just taking R and U to be the minimum arguments of float entropy. And then this here, this is what you use in practice, because you won't necessarily know what the probability distribution actually is for a system, particularly something like the brain. So instead, you just take observations of your system, if you can, and you build up a set of observations And then this, if you're, I call it the set T for typical, so typical states. If your set of typical states of observations is large enough, then this should be close to this. Okay. So moving on. So one slight issue with expected float entropy as an objective function is quite expensive to actually calculate. So the computational work required scales like the number of systems, all possible system states squared. So it's a good idea to try to find some surrogate functions which are much, much computationally cheaper. These suggestions, candidates, scale like 2 times the number of all possible system states. So it's moved that from being an exponent to being a factor. So they're much cheaper. I'm still working on this. I'm still kind of, the important thing is that they must be positively correlated with expected float entropy near the minimum. That's the important thing. But so this is work in progress at the moment. And just a few observations then. So the formulation of EFE as an entropy ensures that we find relationships that have particular relevance to the more probable states of the system, whilst avoiding relationships with relevance to large numbers of arbitrary states that have nothing to do with the system. So that's why it's formulated in this way. EFE is being minimized in U and R simultaneously. So it's a simultaneous optimization that we're doing. And then at the bottom here, I'm talking about comparison with Shannon entropy, or conditional Shannon entropy, which, yeah, okay. It's not so important, but anyway, it's correct anyway. I want to move on to the next slide. Okay, so this is kind of like the main proposition of the theory, I suppose. So the main statement of the talk, I guess. So suppose you have a brain region that's biased to being in certain states, and that can be represented as a probability distribution. And then there's this thing here. Suppose your brain region strongly determines relationships that minimize EFE, and similarly minimize expected multi-relational float entropy. We'll come back to this later. This is to do with higher relationships. Strongly determines, that'll become clear in the next few slides what that really means, but it means that it picks out the relationships well, in some sense. I'll explain later. Then it is proposed that a brain state in the context of these relationships has meaning in the form of the relational contents of the associated experience. So that's basically what it's about. You can actually also use exactly the same theory and also get relationships on the system states as well. So our system states are like functions. You've got relationships on the common domain, on the common codomain. You can also get relationships on the set of functions themselves just by going to evaluation functionals. So that's just, I'll just drop that in there. Okay. So examples, right. So in lieu of actual data for the visual cortex or other things, we will just use synthetic data just to show, because this is a general theory, so it can be applied to all sorts of things. And so we can apply it to photographs. So here we got a stack of 400 photographs, and we take 9 nodes in this kind of sampling orientation. We sample all of those 9 nodes for all of the 400 photographs. And these photographs, they just have a 4 node states. So there's only 4 different color shades of gray here. And we apply expected float entropy minimization to it. And what do we get? We get U and R. And I've put these down as weighted graphs here, so that makes it much easier to read them. But basically, without assuming any relationships between these points at all, we've recovered all of the relationships which give you the geometry. So you can imagine if you did it for a whole photograph, every point, then you would have recovered the geometry of the field of view. And we also recovered the relationships between the colors as well, or the shades of gray in this case. So black is very close to dark gray is between black and light gray, etc. And then there's also this thing down here. So what's this? This will explain a bit better about what I mean about strongly determined relationships. So this is a histogram. What we can do is we can choose relationship parameters uniformly at random and just use those and calculate expected float entropy values for our system. And then we can just build up a histogram of those EFE values. And so that's what this is a histogram. And you can see that when you're just choosing relationship parameters at random, you end up with EFE values up here. So they're all stacked up here. It was 20,000 observations used, they're all here. But when you actually do the minimization, you look for the relationships which minimize EFE, you'll end up right down here. So this is really isolated from other choices. It means that these relationships are strongly determined by the system in some sense. Okay, so that's that one. We can do the same with color images. This is just kind of, uses just two colors, so green and red, and then some intermediate colors between green and red. And actually, this was the relationships between the colors that gave the minimum. So that was a guess, and then we actually found that it was more like this. So basically it extracts the kind of relationships which you're experiencing. So I think we'd all agree that this color here is much closer to these colors than it is to this color or this color here. So it kind of picks out the right relationships. And it's interesting, I think, that therefore the relationships between these things, they're there in the system in some sense. The system itself is defining these things. Okay. So what about a system where we just take samples at random? So we just, instead of using photographs, we just generate random system states. We just choose system states at random. So here we took sort of 200 system states which we chose uniformly at random, and then we did a EFE histogram here, and we found that the minimum, there is still a minimum, so it still has a left tail on the EFE histogram, but it's much, much closer. It's not very distinct from the others. So here it's sort of 7.9-ish, and this is 8.5. So sort of 0.6 difference, whereas here we're right down at close to 7, whereas up here we're at 15. So on the next slide, this point here is much more like around here somewhere. So it's not picking out relationships. And if we actually go to the limit, so we don't just take 200, we take thousands and we go to the limit, then actually the left tail drops off altogether. And so now this isn't, so basically we don't have a left tail anymore, so it's not going to be convergent at all. Okay. So in some sense, there's a kind of zombie type situation, I guess. So we talked about EFE as an objective function. Well, this is a kind of one parameter plot of EFE values, and you see it's almost flat. So it's not going to pick out any relationships. So you're not going to have any meaning. You're not going to have any context. Whereas this example here, we've got a clear, when we do the minimization, yeah, there's a clear minimum here. So this is going to actually pick out, so in this particular parameter around 0.6, that's going to be picked out. So I've got a lot of text. So a couple of predictions on this slide. So we're just basically saying that the first prediction is that for systems to be conscious in the context of this theory, they should have they should isolate relationships strongly. They should not be zombies. And then with regard to the brain, well, maybe there's some parts of the brain where the information is very compressed. When you do data compression, you increase the randomness, it becomes more random. So this kind of suggests that we should find consciousness in parts of the brain which are either pre or post compression, if that is going on. So there's a couple of predictions from this piece of theory, which, you know, may be of interest. Okay, so this actual approach itself is a kind of machine learning approach. So we're doing this minimization. It's a kind of machine learning in order to extract the relationships from systems. So the theory is that the system itself is defining these relationships, but EFE minimization is a method for relationship extraction, if you like. So how well does it actually perform as in terms of sort of machine learning? Well, took 400 photographs, sampled 9 nodes again, and had 4, we've seen this before, 4 node states. And initially, what happens if you, so what we did is we got these 9, we have a training set, and then we have the test set. And the test set, we've removed 4 of the 9 node states. So we need to do, it's a completion task. That's what the problem here is. We need to complete the missing data. And if we just pick them at random, then you just get the binomial distribution. You can see that you get hardly any that pick them all correctly. If we, instead of doing that, we say, okay, for each node that we don't know, let's just choose the most common state that we find. And then if we do this, we do a little bit better. So here we've got 4 of the missing states all completed correctly, but it's only down at, say, 5% still. Most of them have got 0 of the 4 missing states. Yeah. So minimum float entropy minimization does much, much better. We can see now that we're up to sort of getting up for 0.4 or 0.38 of all of the photographs that had all 4 of the nodes correctly completed. However, we can still do better. So if we go to the neural fitting tool in MATLAB, so this is actually applying a neural network to the problem instead. We see that this has done a lot, this is still done better. So now we're up to having completed about 55% of the photographs correctly. So this is telling us that there's still more to do. So the relationships which we've got are very useful, but there's clearly more relationships which we can extract, which then takes us on to secondary relationships. So we've got geometry, we've got color, well, we've got the relationships between colors. And, you know, we can apply it to other brain regions, the auditory cortex and so forth. But there's also things like relationships between objects and so on. So this is why this is showing that we can still do better. So sorry about the text on this slide, far too much text. This is basically float entropy again, but it's a generalization. It's got more relationships added. So the first condition here in its definition is the same as for float entropy as usual. So it's this continuity one. But then we add extras here, and we're applying it in a similar way. And these can be relationships. Structures such as tuples of the initial nodes, so subsets of the initial nodes, nodes that are functions of the initial nodes, ultimately sounds, objects, locations and places, and so forth. And actually this is where perhaps also this bit of theory starts overlapping with some of the other talks that we've heard about, where they start introducing category theory and this kind of thing. And in some sense, I mean, that's all to do with relationships as well. And in some sense, we're all kind of trying to mine the same information. We're all trying to get to the relationships using mathematics to find those relationships and so forth. I think one of the strong things about expected float entropy minimization is it actually gets you started. It gets you the geometry, it gives you the sounds, it gives you this kind of thing. And then you can perhaps find that these other bits of theory can start working at the kind of higher relationship level. Okay, so how's about actually applying this to the brain? So you need brain data. You need data about the states of, say, some level in the visual cortex, V4 or wherever it is that you think is most likely to be useful to look at. It's not easy to do, so these microelectrode type things might be a good way to do it. fMRI, collecting the data that way, it's difficult because the resolution is so poor, but maybe it's possible. Well, it will certainly give you relationships. It's just that you're comparing relationships between cities rather than neighborhoods or houses or whatever. So it's, and then another approach, however, is to model brain regions. So a bit like what Pete was talking about, but the objective is this morning. So, but the objective is different here. So you look at what the literature says about a particular cortical region, and you build a model for it. You let your model run, and then you can sample that. And that might be a good way of collecting data, which you can then apply expected float entropy minimization to extract relationships. So something else that just falls straight out from this piece of theory is isomorphisms, relationship isomorphisms. So I've got a bit of time to explain this, which is good. So you look at this image here. I've got a cyclist in a red shirt, and there's a red flag on the barge, or whatever it is. Maybe it's a traffic cone, I can't tell, whatever. And we would say that, yeah, the red of his shirt and the whatever that is, the flag or whatever it is, they're a similar color. They're certainly more similar in color than with the tree up here, say. And then we can apply some kind of permutation on the colors. And this is actually preserved relationships. So his shirt's now green, and the flag is kind of green as well. We'd agree that those are kind of quite close together, and so forth. So that's a kind of relationship isomorphism. And so when you're looking at your colors, that you can kind of rotate the color space, if you like, and the relationships stay the same. It's kind of invariant. Where does that come from? Well, you can think of your brain state, your brain states or your states of your system as being functions. As I said, you can think of them as being a list. So well, maybe I could actually do it. So these are your system states, your rows, and this is the state that the node is actually in. So U20, U3, and then, I don't know, U5. So you just imagine this is all filled out here with the states that each neuron is in for this particular system state. Well, what you could do is just have a permutation on these node states. So you could just say, whenever I get a 20, I'll swap it for a 3, and vice versa, for example. And suppose before you did that, you applied expected float entropy minimization, you got out your relationship, your weighted graph, and you found that the solution was unique. So there was only one solution. But suppose when you do this transformation of your list by changing the values here, it turns out that you can actually then get back your original list just by changing the order, just by, there's something down here which turns into this, and I can move it up here, and so on. Then it must be that the relationship which solved the initial problem is going to solve the new problem as well with the, because so basically you've got two solutions, but they must actually be the same solution. And in terms of the relationships, what's going on in the relationships, you can see therefore there must be a symmetry because the answer is unique, and so forth. I haven't explained that very well, but hope you've kind of got the gist of what I'm trying to express. So basically such isomorphisms just drop out. It's there in the data, and there's also mirror image as well. So finally, there are some questions down here about when is a system actually a system. So it's kind of an interesting point, I think. So if we imagine our stack of CDs going back right to the beginning, why are these CDs actually associated to each other? You know, they're not. I mean, it's basically, in this case, we're just an external observer, and we're deciding to take the set of CDs as the states of our system to which we can apply expected float entropy minimization. But actually, the stack of CDs, it could be divided into two stacks. It could be spread out across the galaxy. You know, there's nothing really to say that these things should be associated together. So there's this question then, when should we actually say that a system is defining states that belong together as opposed to an external observer just deciding that these states belong together? And this question, I think it ties into also, it has sort of analogies with this issue about when is something actually an observer in quantum mechanics, that kind of thing. So there's some analogies there, perhaps. And one answer is, well, maybe it doesn't matter. Maybe things all over the place are defining relationships. It's just that they're private, so we don't know about them. And even if we did know about them, then the relationships they define, they're nothing like what we would think of as being consciousness anyway. So, but maybe it's going on all the time. We just don't know about it. And then the other point of view would be, no, that's not right. There has to be something which ties these things together and says, actually, these things belong together, and they constitute a system in some sense. And therefore, it's these things which will be defining relationships and will themselves be responsible for that, and therefore be adding to the sort of relationship content of experience, that kind of thing. So there's some questions there. Yeah, so I think I'm a little bit ahead of time, maybe 4 minutes or so. I'm on the clock, but I think I'm pretty much there. So I'll probably wrap up there and let people ask questions if they would like to. So thank you.